everyone, myself Shweta Shah and I am your instructor for the subject Microprocessor and Microcontroller. In this subject we have started Unit 2, that is Architecture of Microprocessor 8085 and Microcontroller 8051. In this unit session we are going to see the pin diagram of Microprocessor 8085. So let me see first what are the topics that are going to be covered in this session. These are like 8085 pin diagram, then pin diagram description, and then we will see the address and data buses and status and control signal from this pin diagram block. Okay, so let me first see what is the pin diagram for microprocessor 8085. It is the basically 40 pin DIP structure. DIP means dual inline packaging. That means it has a same number of pin on both of the side. Here 20 and here 20. Total 40 pins structure. Okay, and this arrow indicates this is the input for this processor unit, and this arrow indicates this is the output for this processing unit. Okay, and if we consider this pin structure, then it is of 40 pins. This is X1 and X2, reset out, SOD, SID, trap, RST 7.5, 6.5, 5.5, INTR, INTA, AD0 to AD7, then VSS, VCC, hold, HLDA, C clock, reset in, ready, IO, M bar, S1, VPP, RD bar, WR bar, S0, A15 to A8, and that's okay. So this is the basically 40 pin structure, but if we try to understand this pin individually, then it will be very tough. Okay, and if we group these pins, then this task will be easier. Okay, so this is its functional pin diagram. In this we have divided whole pins in groups. We have basically divided it into a 6 group. First group is the address bus and data bus. Second group is the control and status signal. Third group is the externally initiated signals and externally acknowledgement signal. Then next group is the serial IO group, and last group is the power supply and clock signal generation group. Okay, we will see each and every group one by one. If we see pins individually, then it will be tough. So let me see group by group, and I have written over that the number of that pin, so you can here in this pin diagram, this 8085 is the 8-bit general purpose microprocessor, and it can address 64 kilobyte of memory that we have already seen in the features. It is the 40 pin DIP structure and uses the 5 volt for power supply, and it can run maximum on 3 megahertz frequency. And this pins are basically divided into 6 groups. These are like address bus and data bus. Second one is the status signal and control signal group. Third one is the interrupt signal. Fourth one is the power supply and clock group. Then serial IO signal group and externally initiated signals. Okay, we will see one by one each and every group. So first we will start with the address and data buses. So address buses are on the pin number 21 to 28, where you have represented higher order address bus A15 to A7. Totally it will require 16 bits. These are like A0 to A15, but we have multiplexed. Lower order address buses are multiplexed with the data buses. So we will see this in that group. Here we are considering whole address bus. So these are like A15 to A0. This address bus has a 8 single lines. These are like A8 to A15, which is unidirectional, and other 8 lines A0 to A7 we have multiplexed. So this is your basic structure for the address bus, that is A15 to AD0. Here A15 to A8 are individual, then AD7 to AD0 are multiplexed with the address and data bus. Okay, so this is the basic structure, basic 16-bit address. And next we can consider as a data bus, or you can consider it as a multiplexed address and data bus, that is on pin number 19 to 12, that is used to save the number of pins, as a lower order address buses are multiplexed with the 8-bit data bus. So here we have AD0 to AD8 as a bidirectional and it also serves as an address bus as well as the data bus. But during the execution of the instruction, these lines carry the address bit during the first part, or you can consider it for the first clock only. After it will carry the data. Okay, and to bifurcate this, we will have one extra pin that is known as a ALE pin, address latch enable pin. If we consider this on the diagram, then this is like this. This is your higher order address bus, and this is lower order address bus. This is AD0 to AD7, that is multiplexed address and data bus, and A15 to A8 higher order address bus, that is unidirectional. Okay, next we will see the status signal. This is basically ALE, S0 and S1. This is your status signal. And next this IO, M bar, RD bar and WR bar. These are your control signal. Okay, from this let me first see this status signal, that is ALE, S0 and S1. Okay, this pin indicates the status of the processor. Here ALE is the special pin that is on 30 number position, that is used to demultiplex the address and data bus. Whenever your ALE pin is 1, that indicates that your AD0 to AD7 lines contains the address. Because we know that AD0 to AD7 can contains address as well as the data. But whenever your ALE pin is 1, that indicates that AD0 to AD7 contains the address. And when ALE pin is 0, it indicates that your AD0 to AD7 contains the data. Okay, and generally this will be 1 at the first clock only. For your instruction cycle, at your first clock only, this ALE pin will be 1, and this signal can be used to enable the latch to save the address bits from the AD line. That we will see how we can demultiplex the AD0 to AD7 lines. At that time we will see this ALE pin is going to be used to enable one latch, and that latch, due to using that thing, we can demultiplex the data. Okay, or you can say demultiplex the address and data bus. Second status signal is the S1 and S0. These are at pin number 33 and 29. The signals are used to specify what kind of operation is being performed at that time. Okay, and usually for smaller system you can't use that, but by using this signal you can find out that which type of task is done, like memory read is done, memory write is done, IO read or IO write is done. So like this, if your S0 is 0 and S1 is 0, then your hold operation is done. Then if S0 is 0 and S1 is 1, then writing operation is going to be done, or writing operation is performed inside the processor. If 1 0, then read operation is done, 1 1, then fetching operation is done. So by using this 2 pin S0 and S1, you can represent or you can find out which operation is being performed right now. Okay, so for this we have to also combine with some control signal. To know actual operation, we have to combine the status signal with the control signal, and then we can find out. Then so next let me see first what is the control signal. Here we have total 3 control signal, that is IO, M bar, RD bar and WR bar. Okay, so let me see what is these signals. And this is the first signal is RD bar, that is active low. You have written RD bar, that means whenever it is active, its value will be 0. Otherwise, its value will be 1. That is the first one. RD bar is used to read memory or the IO bar. Basically, it is used for the read operation, and it indicates that data to be read either from the memory or the IO device, and data bus is ready for the accepting data from the memory or the IO device. Second control signal is WR, or you can say write bar. WR bar, here it is bar, that is not indicated, but it is WR bar, that is active low signal. That is the write memory or the IO device, and it indicates that data on the data buses are to be written onto the selected memory address or the IP device, or you can say IO device. And third control signal is IO, M bar, that is input output / memory, but memory is the active low. It has a dual purpose. If its value is 1, that means it is for the IO. If its value is 0, that means it's for memory. Okay, so the signals specifies the read and write operation related to whether memory or the IO device. When its value is 1, the address on the address bus is for the IO device, and when its value is 0, that means it is a memory related task. So this address is related to the memory. If its value is 1, then your address is related to the IO device, and if its address value is 0, that means your task is related to the memory device. Okay, so we can use this IO comma M bar, read, write, and that status signal combinedly to generate whether you have to write in memory, read in memory, or write in IO device, or read IO device. Whatever task you want to generate, you have to combine all of these things. Okay, so let me see how you can represent this. Here this IO comma M bar, that's when its value can be 0 or 1. If it is 0, then its task is IO related, and you have RD bar or WR bar. If your device is IO or memory, you have to do only two tasks: read the content or write the content, or read the data or write the data. And that location, or you can say that address, is provided on the address bus. You have to perform some task of reading or writing on the data that you have already provided, address you have already provided on the address bus. Okay, if its value is 0, IO comma M bar is 0, and RD bar is 0, and WR bar is 1. Here RD bar and WR bar are active low, that means whenever its value is 0, that means it is active. Here RD bar is 0, that means your read task is active, or read control signal is active. That means you have to read, but you have to read what? You have to check IO comma M bar. If it is 0, then you have to read the memory. If it is 1, then you have to read the IO device. Okay, so if it is IO comma M bar is 0, RD bar is 0, and WR bar is 1, then you have to do the task of reading, but of what? Of memory. If it IO comma M bar is 0, RD bar is 1, and WR bar is 0, that means you have to do the task of writing, but of what? M is 0, that means you have to write in memory. So it is your control signal memory write. You have to generate the control signal, that is memory write. Here you have to generate the control signal, that is memory read. Similarly, if you have IO comma M bar as 1, that means your task will be related to the IO device. Okay. And if RD bar is 0, that is your control signal is generated is RD bar, then that means you are doing the IO read task. And if RD bar WR bar is 0, then you are doing the IO write operation. Okay, so this is the basically how you can generate the control signal for reading the memory, writing the data into memory, reading data from the IO device, or writing data into IO device. This is your control signal. Address is already provided to you on the address bus. This is your control signal, and after getting this control signal, data will be provided onto data bus. Whether it is memory read or memory write. If it is memory read, then you are providing the data from memory to the CPU. If it is memory read, then and only then. If it is memory write, then you will provide the data from CPU to the memory location. Okay, address is on address bus, data will come on data bus, but these are the control signal which require to perform that task. Okay, so we can combine this control and status signal to know actually which operation is done, which operation is performed over here. So whenever we combining this S0, S1 with IO comma M bar, we get total 8 combination. Here we have total 3 signals, that is S0, S1 and IO comma M bar. If we combine these 3 bits, then we will get total 8 combination, and that total 8 combination tells us which kind of operation or which kind of machine cycle is right now executed or right now run by the processor. Okay, so if we consider this, then it can be combined like this. First we will write IO comma M bar, then we will write S1, and then we will write S0. Here total 4 combinations for S0, S1 are possible, that we have already seen. Like if it is 1 1, then fetch operation is there. If it is 0 1, then you have done some. If it is 1 0, then you have done read operation. If it is 0 1, then you have write operation, and so on. That we have seen in the first table. Okay, and that we are combining with the IO comma M bar that we have seen over here first in this table. Which kind of operation is done by the processor, if it is 0 0 then halt operation, if it is 0 1 then write operation, 1 0 then read operation, 1 1 then the fetch operation is done. But of what? Of memory or IO, that you have to combine with the IO comma M bar. Then we can say whether it is memory read or IO read, whether it is memory write or IO write, whether it is opcode fetch or other thing. Okay, so this we have to combine with this 4 signals. So if it is 0 1 1, that means this task is of opcode fetch, and it will for fetching the opcode, that is you have already stored inside the memory. That means you have to read the data. So for that task you will require the RD bar as a 0, that is your read signal. If it is 0, IO comma M bar is 0 and S1 and S0 is 1 0, that means memory read operation, and for that also you will require the RD bar 0. And if it is 0 1, that means memory write operation, and for that you will require the WR bar 0. That means you will require control signal write for write, control signal for read. Okay, opcode fetch means fetching the instruction. Opcode fetch, that means fetching the instruction from the memory. That is one kind of memory reading task, but reading the instruction rather than the data. In memory read we will read the data, okay, but in opcode fetch we will read the instruction. Control signal will be required is of read, but reading thing is different. In memory read, that is the data. In opcode fetch, that is the instruction. Okay, if your IO comma M bar is 1, that means your task is related to the IO. And if status is S1 is 1 and 0, that means this is for read. And for what? IO. So this will be your IO read task. And if it is 1 0 1, that means your IO write task. For your IO read, you will require RD bar signal, and for IO write, you will require control signal as a write 0. So this is your basically control signal, and you will combine this with this, that is your IO read or IO write control signal. Similarly, if we see the next combination, that is IO comma M bar is 1 and S1 is 1 and S0 is 0, then this is indicating the interrupt acknowledgement, and for that you will require the INTA bar equals to 0. That is the interrupt acknowledgement signal. After you have acknowledged the interrupt, you will generate one control signal, that is I have read this instruction. Processor will tell that I have read this interrupt, and it will acknowledge with the INTA bar as a 0. This is also active low signal. Okay, that is we are going to see in another pin group, that is the interrupt group, that we will see this. It is the active low signal. And last group is the for S1 and S0's value is 0 0, and at that time your IO comma M bar is at Z. Z means at high impedance state. You are considering it as a not connected. Okay, if it is 0 or 1, then you can use like for the IO or memory, but if it is in a tri-state mode, that is you have not connected it and its value is 0 0, then your hold operation is performed inside the processor. So by this way we can see how we can use the control and status signal for the pins. So we are ending our today's session over here. Remaining groups of pin we will see in the next session.